Okay, good morning. Let's get started today. This is week 5 of classes. Um, we are now starting to look at, things that we can do with LPs. What are some of the additional information that we can get with LPs? So this week, my focus will be on two topics. So today's class, I will talk about, or we will discuss sensitivity analysis, and then for Friday's class, I will talk a little. We will discuss a little bit on ideas related to solving large scale LPs. So when problems are really big, what are some ideas that you can employ algorithmically to solve very big LPs? Okay, and just a quick reminder: next week is the midterm. It's on the Friday. It will be a 2 hour test. Okay, from 10 to 12. It's the same timing, and uh, I haven't as yet looked at your assignments, and you will be submitting your second assignment this next week. That is week 6, right? Next week is week 6.
Yeah.
Yeah. This is week 5, so week 6. The next Friday is a midterm, and most of the coverage for the midterm. I think I'm just thinking of the paper right now. So I mean, the things we'll cover this week will be building on ideas we have used before. But I guess I'll probably be testing you up to week four's material primarily. But whatever we do this week, it's still building on these ideas. So only if you understand this, it's going to help you. It's going to anyway reinforce your concepts. Also for the midterm, I'm thinking I will you can bring in a couple of sheets of paper if you want with handwritten notes or whatever, things to just help you, maybe some formulas or maybe some transformations of primal duals and stuff like that. So two A4 sheets, both sides you can write on. If you want to write some notes down, you don't want to write anything, that's fine. So think of it like a help sheet. You can get whatever you want for two sheets. Okay. And so it'll be a 2 hour test. Okay. That'll be on the Friday. Is that a question? Sorry. Yeah. No? Is it too quick, the midterm, or you're not ready for it? Okay. Okay. Yeah. So next week, Wednesday's class, I will not take. So I will not teach. So I will just have a look at your assignments. If I think that the assignments, there are a lot of difficulties, or then I will maybe review some of the assignments next Wednesday, or maybe we'll cancel the class. Okay. So you can just prepare basically next week for the midterm. Okay. Okay. Is there any other question about before we go ahead?
The topic in the midterm exam is cover till
So I will not probably, I'm still setting the exam, I'm still setting the midterm. So I will probably not test you on the material that we are doing this week. What we are doing this week, I will probably not test you. That's my feeling right now. So if I change my plans, I will let you know. But at this point, you can assume I will not test you on the material this week. But, yeah, that's fine. Yeah. It will be, so the assignments are an example of the type of thing. So you will not, yeah, so it will be more. So I think the assignment questions are an example of the type of things you can expect, the homework questions. So it'll be a mix. I will try to figure out if you have a good understanding overall, from formulation to, understanding, solving problems with, do you understand the simplex method? Do you understand duality? So I'll be testing on all these things. Yeah. So I think the assignments are a good indication, but of course it won't be a exact replica for an assignment question. Okay. But I would say it would be yeah. So you would not, so, okay. So for example, you won't need things like calculators for the exam. So there'll be no calculations which are like complicated to do if there are any calculations at all. So there'll be simple calculations. Okay. Nothing will be like crazy numbers or things you can do in your head, basically. So I will not be testing you a lot on, complicated algebra or, doing lots of, so of course, if you do simplex and stuff like this, it'll be some simple steps. It won't be like, yeah, I'm always more interested in concepts, basically. Yeah. But there will be some, yeah, but there'll be no, yeah. But I think the assignments are a good example because assignments we have covered, I think there's a mix of things I've given you. Yeah. Okay, good. Anything else on the midterm? Okay. So this week's material. So just to give you a heads up where we are. So we have completed last week duality. That's probably one of the most important topics in optimization. The fact that linear programming has a very nice dual class of problems, and there is a very strong connection between the primal and dual. This is a very important idea for linear programming and more generally convex optimization. So it's sort of a non-trivial idea. And today, what we'll do is we will think about, from a practical perspective, what are some other things that you think about when you think about LPs. So our goal today's class will be to discuss. So I'm going to be focusing on, sorry, uh, sensitivity analysis. I will explain what this means. Okay. So as the word sensitivity indicates, it's about how sensitive the problem is to the changes in the data. Okay. So let's think about what is LP. Okay. So let's take an LP in standard form. So let's say I'm giving you a linear program in primal form, which is to minimize C transpose X subject to AX equal to B, X non-negative. Okay. Now remember that in most practical applications, a company, for example, there are companies which solve LPs and even integer programs on a daily basis. You're doing some shipping, routing, you're doing, some revenue management on your airline networks. You're solving LPs. Okay. And they might be solving this once a day, maybe multiple times in a day, or, depending on their planning horizons. Okay. So what is the input for an LP? The input are essentially three things. You have a matrix A, a vector B, and a vector C. Okay. And of course, this will depend on the context of the problem, what your decision variables are, and what your data is. And so this is the data which you either, you have to estimate, you have to collect, this is an input to your model. What's my output? My output is X star, my optimal solution to this problem. And also once I know my optimal solution, I also know my optimal objective value, which is the cost. Let's say I'm minimizing cost. It's my cost. So this is my optimal solution. And that's my optimal objective. Okay. Okay. Now we are solving an instance of a problem, but in reality, the data might fluctuate, might change a little bit. So for a given A, B, and C, I solve the problem, I get an X star. But if the data changes a little bit, what happens to my optimal solution? Does it change or does it not change? If so, by how much does it change? Can I get a handle on this? Okay. So what sensitivity analysis does is essentially it answers questions of the following type. Suppose the input changes. Okay. And we will look at different types of changes today. But essentially, you think about, I take A, I've got an original A, but maybe there's a perturbation in A, which I'm writing as delta A. Or maybe there's a perturbation in B, delta B, or a perturbation in C, let's call this delta C. Okay. And we will look at different types of perturbations today. So suppose this input changes, then the question is, does the optimal solution change? Okay. Does the optimal solution change? Okay. Okay. For what perturbations does it remain the same? Okay. So clearly you should expect that if the perturbations are small, they're very small changes, maybe the optimal solution won't change drastically. But maybe if the perturbation is large, maybe the optimal solution is very different. Okay. And then can we resolve the problem quickly if it changes? Okay. So this is the type of questions that sensitivity analysis will answer. Okay. So to try to tell you, suppose something changes in the optimization problem a little bit in the input, maybe your solution is not going to change and is going to give these numbers to you. Or maybe if your changes you're expecting is a lot more, then maybe you have to resolve the problem. Can you use some ideas on how to resolve the problem quickly? Okay. But this is not only for LPs. Okay. You can think about any optimization problem. How sensitive is your optimal solution to changes in the input, basically? Okay. And can we measure this? And how can we use our algorithms to deal with this, to predict what the changes are going to be? And can we also give this as an output? So if I solve a LP today, any software, any good software will give you a sensitivity analysis report. It will tell you that if things change in this range, your solution will not change. Okay. And I will show that to you later. Okay. But this is more important broadly for any optimization problem. You want to understand how sensitive your solutions are to a change in the input. Okay. And there are some other ideas. Okay. If I have time at the end of the class, I'll tell you some idea on robust optimization, which means that you're trying to find a good solution even when there are changes. So when you're implementing your solution, you don't know if your data is going to change a little bit. So you are still implementing your solution, so you still want a good solution. Okay, so there are some other ideas which I will talk about as we go through. Okay, but for now we'll talk about sensitivity analysis. How does this change affect the optimal solution? Okay, okay, and the most important thing is we are going to use. So everything we are going to do today is going to depend on our what we know already for LP. So the beauty of LP is we have got very strong conditions, or we have very crisp conditions to explain what an optimal solution looks like. Okay, so recollect. So recollect. B is an optimal basis. So it's a subset of this matrix A, square matrix, which is invertible. If they satisfy two conditions, one, B inverse B is non-negative, and two, the reduced cost vector, which we defined as C transpose minus CB transpose B inverse A, is non-negative. Okay, everything boils down to these two conditions. Okay, so these two conditions are key to LPs. Okay, because we know for LPs, if I have these two conditions satisfied for a basis matrix, it's optimal. Okay, as I change my input, these conditions are going to get affected. So we'll have to figure out what happens to these optimality conditions. How do the optimality conditions change as we change something in the input? Okay. And of course, you should, so this is for a primal optimum. So remember, with the primal, there's a dual problem. So we're looking at a standard form LP. So my dual is to maximize P transpose B subject to P transpose A less than equal to C transpose. So we know now that the optimal primal is B inverse B, the basic variables. My non-basic variables are 0. So that's my primal optimal solution. And my dual optimal solution, P star, is basically the transpose of this is CB transpose B inverse. Okay. This is the whatever B, if I find a B which satisfies these two conditions, this part gives me the optimal dual variables. Okay. So we know these two, and everything is going to boil down to using these conditions today. Okay, so these two conditions are really, really important for LPs. Okay. Okay. So this is just a recap. So I'll take an example and we'll work. So what I'll do is I'll show you, I'll give you an example. I will tell you the theory and then we'll go back and look at the numbers just to get a sense. I'm not sure we'll get through everything, but I'll give you enough of a sense of what sensitivity analysis does. Okay. Okay. So let's take an example today just to, I'm just going to give you a motivating example with some numbers. Okay. So let's say I've got a manufacturing problem. Okay. Okay. So you're trying to manufacture, let's say, 3 types of furniture. Let's say beds, tables, and chair. So you're trying to manufacture this stuff. Okay. You have to each of them gives you a profit. And I'm just going to give you some numbers here. So let's say it's 52, 30, and 20. Okay, so this is my profit. This is in dollars per unit. So every unit of bed I sell, that's my profit, and so on. Okay. Okay. So I'm going to have to figure out how much beds I make, how many tables I make, how many chairs I make. Those are my 3 variables, X1, X2, and X3. And what you have in these manufacturing problems typically is when you're manufacturing these items, each of these items requires some amount of resources. So you're going to have So we look at an example with three types of resources. So you have to manufacture. So you have to do manufacturing. So this is the actual manufacturing of the so the actual manufacturing of the good. Okay. Then maybe you have to do packaging of the good. Okay. And then maybe you have quality assurance. So you have to check, you have to do some quality testing on this. So each time you manufacture something, there are multiple processes, multiple steps. Let's imagine a problem where there are three steps. Okay. And you have a certain number of man hours available for for each of these resources. So let's say you have 204. So what is the units here? Let's say man hours. Okay. So I've got people employed. They work for a certain number of hours. So number of people times hours. So I've got, let's say, 204 man hours available for manufacturing. I've got 100 man hours for packaging and 30 man hours for quality assurance. Every unit of bed that I make will require a certain amount of manufacturing, packaging, and quality assurance. So I'm giving you some numbers here. Let's say 10 to 1, 5, 4, 1, and 251. What is this? Every for manufacturing a bed, one unit, I require so many man hours per unit. So these are all in man hours per unit. Okay. So what's my problem? I want to manufacture items. Of course, I would like to manufacture infinite number of beds, tables, and chairs. I'll get infinite profit. But I can't because I've got only a certain number of resources available for me. I can only manufacture up to 204 man hours per, let's say this is for a particular unit of, let's say for a day. Okay. Okay. So that's the problem. Is that clear? What we're trying to do? Okay. So let's write the LP. I won't solve it. I'll just give you the optimal solution. So I'm trying to maximize, okay, the profit, okay, 52x1 plus 30x2 plus 20x3. Now, because we have developed our theory for minimization problems, okay, I'm just going to write everything in a minimization objective form just for keeping consistency with the theory. Okay, so instead of maximizing the profits, I'll minimize the negative of the profits. Okay, so it's minimizing minus 52x1 minus 30x2 minus 20x3 subject to my constraints, which is 10x1 plus 5x2 plus 2x3. Okay, this should be less than equal to 204. Okay, and clearly all these numbers have to be non-negative. Okay, that's my problem. Okay. Okay, and let's say when you solve this, how would you solve this? So this is a problem where it's easy to find a starting basic feasible solution. I would simply I'd add three slack variables here, set them to be those numbers, set all x1, x2, x3 to be 0, and then I would apply a simplex method and solve it to optimality. Okay. So let's say I give you the optimal simplex tableau. Okay. So I'm just going to give you the optimal tableau. Okay. So let's say it's x1, x2, x3, and I've got three slack variables, s1, s2, and s3 for these three constraints. Okay. So if you solve the simplex to optimality, you will get a solution which looks like this: 0, 2, 0, 4, 0, 12. You can check this at your own time. Okay. So our goal today is not to go through the simplex method, but to understand sensitivity analysis. Okay. So you'll get 18, 4, 12. Sorry, 1 by 8 and 5 by 8. So by the way, it's there in the notes, okay, which I've uploaded, but I just want to write this down once time. Okay, so we have solved the simplex problem. We have used the simplex method, solve the problem to optimality. That's my final tableau. So what's my tableau telling me? All my reduced costs here are non-negative. So I'm at optimality. It says you make X1 star is 18. So you make 18 beds. Okay. And it says you make X3 is 12. So it says you make 20 chairs. Sorry, 12 chairs. Okay. And X2 is 0. So you don't make any tables at this point. That's the optimal solution. The profit of this solution will be 1176. Okay. Fine. So that's my LP. I've solved it. Now we'll look at sensitivity analysis. Okay. So let's start with that. Okay. Any questions here with the form, with the where we are going? So you should be able to solve this problem. Okay. It just takes a bit of time, but you can do this. You will get a tableau which looks like this. Okay. So let's now do sensitivity analysis. Okay. So we're going to do first what is called local sensitivity analysis. That means when there are small changes in the data. Okay. And typically, any LP solver will give you uh, results on this. Okay. Will give you output from this. Okay. So we're going to first start with the first thing we'll look at. So there are three components, A, B, and C. Let's start with the change in the B vector, the right-hand side. Okay. So what is the change in B? So in this problem, suppose I have extra manufacturing hours. I know I from 204, I've suddenly increased my number of workforce. I now have 210 units of manpower. How should my solution change? Suppose it went down from 204. I lost some people. People were unwell. It went down to 190. How should my solution change? Okay. Of course, you can resolve the full problem from scratch. But can you be smart about it and understand from the optimality conditions how to do this? Okay. Do we have to solve the problem for every instance, or can I figure out for what range it won't change? Okay. Okay. So let's say we are changing. So let's say BI. So let's talk about, let's say for now, think about manufacturing time. Let's say BI B1, BI change from 204, it changes to BI plus delta. Okay, so it's changed a little bit. Okay. So this is the same thing as saying you're changing B. So you're only changing the ith component. So this is saying B changes to B plus delta times EI. What is EI? EI is a vector with 1 in the ith component and 0 otherwise. Okay, so I keep using this notation EI. It's a unit vector with 1 in the ith position. Okay, so I'm just changing. So wherever it's 0, I will just get the same B. But for the ith component, I'll get BI plus delta times 1, which is BI plus delta. Okay. What happens when the B changes? There are two conditions. That is the feasibility condition and the optimality condition. Where does small b show up? It only shows up in this condition, but small b does not show up in this condition. The right-hand side vector of LP shows up only in this feasibility condition. It does not show up in this condition. So for example, if I've got a current optimal basis, which I have already identified from the tableau, it will not change these conditions as small b changes, but this will change or can change. Okay. So it's clear that the condition 2, the optimality condition is unchanged. Okay. But the feasibility condition 1 changes. Okay. So for B to be an optimal basis, capital B to be an optimal basis, what do I require? I require B inverse. The B has now changed to B plus delta EI. I require this vector to be non-negative. If this vector was non-negative, the reduced cost vector is non-negative. This vector is non-negative, so it's a basic feasible solution. So it has to be an optimal basic feasible solution. So as long as delta satisfies this condition, the original optimal basis matrix will still stay optimal. Okay. But what is this? This is nothing but a condition, right? So what is, so we, how do we, so we can use star to find a range for delta. Because if delta changes, it tells you for what delta, I mean, each of this is an inequality. It's a vector being non-negative. So the first component will tell me delta has to satisfy some condition. It's a scalar. I get many conditions. It's a scalar value. So I'm going to get an upper bound and a lower bound, basically. Okay. So it's going to give me a range. Okay. Now, another thing here which is important is, if you look at this condition, you should also see that, think about the cost. My original optimal cost was CB transpose B inverse B. If B changes, my cost changes to CB transpose B inverse B plus delta times EI. Okay. What is this? This is the original cost plus delta times CB transpose B inverse, which is the dual vector, optimal dual vector, times EI. You take a dual vector, multiply it with a unit vector, it will take the ith dual variable out. So this is nothing plus delta times pi star. So this gives you another interpretation of the dual variable. What is the dual variable telling you? It is the change in the cost, unit change in cost. So for every unit change in the ith requirement, bi, unit change, how does the optimal cost change? Because if delta is 1 for unit change, the optimal cost will change by pi star in this range. Okay. So this is another, so this is an important interpretation. Pi star, that's why the dual variable can be thought of as the marginal cost, also what's called the shadow price. Okay. For unit increase in the BI component, which is the requirement, right? The right hand side. Okay. Is that clear? The interpretation? So, okay. But this is true only when the current basis is still optimal. Okay. So if delta is too large, okay, this condition, if delta changes too much, this condition could get violated. Okay. So if this condition gets violated, what do you do? Then the B will not, if this condition is not greater than equal to 0, then it will not be a feasible, the original optimal basic feasible solution will not be feasible, because the B has changed too, small b has changed too much. So what do you have to do? Then you have to use a simplex method. So you can then, so if delta changes beyond that range, beyond the range we identify, beyond the identified range, you can simply use your basic feasible solution is no longer a feasible solution. Okay. So you can't use, so of course you can resolve the problem from scratch, but actually you can use here the dual simplex method. Why? Because the reduced cost vector is non-negative. So it's a dual feasible solution you've already got. The primal feasibility condition is violated. So you can actually use dual simplex to solve the problem. Okay. Primal simplex works when you are having primal feasible solutions and you're moving to better primal feasible solutions. Here, if this condition gets violated, I'm losing primal feasibility. But my dual feasibility is still guaranteed, because these conditions are still non-negative. So I still have a dual basic feasible solution. So I can essentially use a dual simplex method here. Okay. Is that clear? Or at least broadly, I didn't go. So remember what the primal simplex and dual simplex does. In primal simplex, this condition is satisfied, but this condition is not satisfied. And you work towards this. In dual simplex, this condition is satisfied, but this is not satisfied. So you work towards this. Why is this useful? Because it just turns out that the algorithm will converge faster, because you already have a good basic feasible solution for the dual problem. You just try to work towards optimality. So typically this works faster. Of course, you can solve the problem from scratch again if you wanted. It's fine. You can do it. Okay. So let's look at, okay, any questions here? Okay, so let's go to the example. Let's just quickly see what happens. So in the example, let's take what is B1. B1 was 204. So now I'm changing B1 to B1 plus delta. I want to know what change of delta allows me to still keep the original the basis matrix as optimal. Okay. So I need to check B inverse B plus delta times E1 is non-negative. This is the condition I have to check. Okay. So I'm changing the resource requirement of the manufacturing hours. This number is changing. Okay. But what is B inverse B? That's my basic feasible solution, 18, 4, and 12. So my current basic feasible solution, my basic variables are 18, 4, and 12. So this B inverse B is 18, 4, and 12. This is B inverse B. I get this from the optimal tableau, right? My optimal tableau is 18, 4, 12. That's my optimal basic variables. Plus delta B inverse E1. What is the basis matrix inverse? So you should know by now what the basis inverse is. So what is so where is B inverse in this tableau? So my current basic feasible solution is 18, 4, and 12. So my basis matrix is what? It's a column of x1, 10, 2, 1, column of s2, 0, 1, 0, column of x3, which is 2, 5, 1. That's the basis matrix. I can invert this and find B inverse. But we know that B inverse can also be identified from the tableau. Where is B inverse in this tableau? Do you remember? What does the tableau keep track of? This part is what? B inverse times A, right? This is what is there in this tableau here, right? Do you remember this? This you should know, right? But A as an identity matrix, which is the slack variables, 1, 0, 0, 0, 1, 0, 0, 0, 1. So wherever the A had an identity matrix in the A matrix, my tableau will have B inverse in those columns. So this is B inverse, this part. You're looking a little bit quizzical. So do you remember this or no? Yes? Okay, fine. If you know it, that's great. I just sense that not some of you were looking a bit quizzical. Yeah, that's good if you remember. Okay, so this is the B inverse. Okay, so remember B inverse is actually there in the matrix. Okay, it's stored in the tableau. So I'm just taking this B inverse and I'm moving it. So this is the B inverse. Okay. And then E1 is what? E1 is simple. E1 is just 1, 0, 0. So I want this to be non-negative, right? This is straightforward. It's going to give me a range on delta. If you check for this, you can validate yourself. Delta will lie between 90. So it turns out, so the first condition will tell you what? Delta 18 plus delta by 8 is greater than equal to 0. So you'll get what? 18 plus delta by 8 greater than equal to 0. 4 plus 3 delta by 8 is non-negative. 12 minus delta by 8 is non-negative. So this gives me if I take this to the other side, it gives me a lower bound on delta, a lower bound on delta. This gives me if I take this side, it gives me an upper bound on delta. So this will be 12 times 8, so 96. This gives me two lower bounds. Delta has to be greater than, less than, so delta, the lower bound is what? Delta is greater than equal to minus 18 into 8, or delta is greater than minus 32 by 3. So whichever is the higher lower bound is what I have to take, because both conditions have to be satisfied. So that will give me minus 32 by 3. So in this range, E still remains optimal. That means I will still make only x1 star, s1, sorry, was it s1 in the optimal basis? S2, x1 star, s2 star, and x3 star remain optimal basic variables. Okay. And you can calculate what these numbers are. It's for any delta in this range, you know what the number is, right? I mean, what is x2, x1 star? It'll be 18 plus delta by 8. You just calculate the number for the delta in this range. So if delta is, for example, delta is 1, it'll be 18 plus 1 by 8. So the new amount of manufacture, the amount of beds you'll make is 18 plus 1 by 8. Of course, fractional numbers don't make sense in this problem, but we are solving LPs here, so let's just live with that. If these numbers are very big, you can always round it. Okay, is that clear with that analysis? So these numbers will be given by back from the LP reports. Okay. So if it changes beyond this, you'll have to use, you can use dual simplex or you resolve the problem. Okay. Any question here or can we move on? Okay. So next we'll do is change in cost. So change in C. Okay. Okay. Now in the change in the objective function, it will depend on if the objective function is changing, the coefficients are changing. So what are we going to do? We're going to take Cj, and Cj is going to be modified to Cj plus delta, which is the same thing as saying the cost vector C is modified to C plus delta times Ej. Okay. So I'm going to take a particular cost objective function component, C vector, a C component, and perturb it. And I want to know for what perturbation does my optimal solution remain the same. Okay, or my optimal basis matrix remain the same. Now it's going to depend on whether the variable is a basic variable or a non-basic variable in the optimal solution. Okay, so remember J corresponds, xj is a variable. It might be basic or non-basic. Okay, so there are two cases here. So this is why you have to analyze the conditions. Okay, so if xj is a non-basic variable currently, so what does it mean? It means xj is 0. Okay, xj is at a value 0. Okay, now let's look at the conditions. What is going to change? So when my C changes, the first condition is unaffected for changes in C. What changes is the second set of conditions. But in this, there is C showing up in two parts. The C shows up here and the C shows up here, but only for the basic. This is only the cost for the basic variables. Okay. So remember, basic variables will always have a zero reduced cost in any tab. We saw this in the third week. If you just plug in for the basic variables, this will give you a formula that says basic variables will always have a zero reduced cost. So actually, you have to check these conditions only for non-basic variables. Okay, the reduced cost conditions. So if the condition, if you're testing this only for non-basic variables, if the non-basic variable changes, it doesn't affect this part. It only affects this part, right? This is only the basic variable costs. So I'm changing the cost of a non-basic variable. Only this part will change, but not this part. Okay. So it's an easier case. Okay. So in that case, what will happen is we need to check what? That Cj plus delta minus CB transpose B inverse AJ is non-negative. We'd only check this condition, nothing else basically, right? Because, I mean, we need to check for B to be optimal basis. Only this condition we need to verify, check or verify. That's fine. Okay, is that clear? If if delta satisfies this condition, then I claim for Cj plus for any value of delta which satisfies this condition, the original basic optimal basis will still remain optimal. Because the reduced, why is this? Because the new reduced cost for this xj variable is still non-negative. And that's an optimality condition. But we know Cj minus Cb transpose B inverse Aj is nothing but Cj bar, right? So this is the same thing as saying Cj bar, the original reduced cost for the jth variable plus delta is non-negative, or delta has to be greater than equal to minus Cj bar. So this is a very easy case. Okay. Okay. Any question there with that? Is that clear? So with as long as delta satisfies this condition, the optimal basis does not change. Okay. The slightly more not complicated, but slightly you have to be a bit more, check a few more conditions is if xj is an optimal basic variable. Okay. Then what do you have to then we have to check. So for B to be still an optimal basis, what do we need to check? We take the reduced cost for all the non-basic variables. But now, remember what the condition is. This CB vector, when xj is changing, this basic variable cost is changing here, basically. So this CB vector is changing, and I'm going to write this as delta times E. I'm just writing this in a particular way. I'm going to write this as delta times Ej of B. I'll just tell you what this what this notation I'm writing as. So what is this? This is, so I'm now thinking about a vector of the dimension of my basic variable. So if I got m equality constraints, I've got m basic variables. So this is a vector of dimension m. And because xj is a basic variable, this is a vector where, so this is a vector 1 if, so 1 for component j in the basis and 0 otherwise. Okay. So remember when I wrote initially delta of Ej, this Ej vector, unit vector was of dimension of n, the total number of variables. But now I'm just writing it for the basic variables. And xj is one of the basic variables. So one of them will be the basic variable. I'll put a 1 there and 0 otherwise. Okay. So what is this saying? I require to check a few more conditions because changes in basic variable costs are affecting the reduced costs of all non-basic variables, not just that. Previously, when I changed a non-basic variable cost, it only affected that condition. But here, more conditions are affected. But it's not particularly hard. These are just, again, just going to give you some upper and lower bounds on delta. So you can identify that to find the range for delta. Okay. So use this to find the range for delta. Okay. And what happens if delta changes beyond this condition or beyond this condition? What happens if the change in the cost is too much? If it violates this condition or it violates this condition, some of the reduced costs are going to become negative. So then just go back and use primal simplex. Just go back and apply your simplex method. It's got a negative reduced cost. Get that variable into your basis, because trying to bring that variable into the basis is going to be a good, is going to decrease your objective function. So beyond this range, use primal simplex. Okay. Of course, you can solve it from scratch again, but remember in simplex we are already moved to. I mean, maybe have started from a original basic feasible solution. They've got a solution to a new problem. Maybe if the perturbations are the optimal basic feasible solution changes, but maybe it's going to be close to this original optimal basic feasible solution. So you're already at some point, so you can just move from that point instead of starting from scratch all the way and going back all the way. Okay. So again, these are algorithmic ideas which are sensible and reasonable to do. Okay. Okay. So let's maybe just implement this for this example. Any questions with this theory? It's simple, but it's elegant. Okay. And it's sort of natural if you think about it. And everything, as you can see, boils down to two conditions. Okay. Essentially, two conditions. You should be comfortable with these two conditions. If you understand these two conditions, you will be able to understand these ideas. Okay. Okay. So let's just maybe just for completeness, let's complete and let's just do this for this example. Okay. So let's say currently, so let's just go back to this solution. So currently, given all my availability of my resources and my profits, I'm not making tables currently. Okay. So currently x2 star is not in my basis. It's a non-basic variable. I'm not making tables. So for what range of changes in the profit will I not make tables still? Or the current basic feasible solution will still stay optimal. So my condition tells me look at the reduced cost for the variable. The reduced cost for the x2 variable is 2. Okay. So we just saw that the condition is what? Cj bar plus delta has to be non-negative. Okay. So for the table, so 2a, so for tables, currently C2 bar is 2. This will be non-negative. So C2 bar plus delta has to be non-negative, which is corresponding to saying delta is greater than equal to -2. Okay. Okay. So what does this mean? This means that in the cost formulation, you can change up to, I mean, any perturbation which is above -2 is okay. Okay. So what does this mean in the, so if you convert this to this for the cost formulation. So in the profit formulation, where it's the revenues, it basically says that if the profit, unit profit rather, if profit per unit table is less than equal to 32, 30 plus 2, 30 was the original number, 30 plus 2, then we stay with current optimal BFS. Okay. If the profit went above 32, 33 or 32.1, 33, 34, 35, I have no guarantees because my reduced cost is going to become negative, and then I will have to start producing tables for a better, I mean, I can start producing tables to get a better solution. Okay. Of course, if you decrease the profit, at a profit of 30, you're not making tables. If you make the profit of tables 20, there's no way you're going to make it. Why will you make it? You're reducing the profit, unit profit. You're not even making it when it's $30, your profits. Okay. So I'm just converting the cost to a profit representation. Is that clear? So these are useful information because imagine for a sales rep, if they are, if they are, no, so at what range do you start actually producing it? So this gives you economic information. Okay. So if we do this now for, let's say, for a basic variable, so let's say, let's take beds. So let's take, so beds is, so currently I'm producing 18 beds. I'll just go back to the solution. I'm currently producing 18 beds. The unit profit is 52 for beds. Okay. So suppose I change the cost for beds. Okay. Profit for beds. Okay. So beds, current production is equal to 18. So I want to know when will I start changing this? Okay. So what are we going to do? So we have to look at this optimality condition. Okay. So take the cost for my non-basic variables. What are my costs for my non-basic variables? My cost for my non-basic variables. My non-basic variables are x2, s1, s3. x2 as a cost of my. Actually, I can write this in terms of. Yeah, maybe I should write this. Maybe I can simplify this. So we can rewrite this condition. I'm just going to rewrite this condition, okay, to make it slightly easier. Cn minus Cn transpose minus Cb transpose B inverse n is just the reduced cost vector minus delta EJB transpose B inverse n. Okay. So this reduced cost vector I already have from my optimal tableau. Okay. So let me just bring this here if you don't mind. I'm just going to bring my optimal tableau here. Let me just cut and paste this. So what's my current reduced cost vector? My current reduced cost vector, these are my non-basic variables. X2, S1, and S3. So my current reduced cost vector is 2, 4, and 12. Minus, what does this condition say? I require the reduced cost vector minus delta, whatever the delta is. I'm going to identify this. The unit vector corresponding to making changes in. So I'm going to try to change the cost of X1, right? So I'm trying to change C1 to C1 plus delta. So this is changing by 1, 1, 0, 0. B inverse n. Where is B inverse n? So remember, this is B inverse A. So I just have to look at the columns corresponding to my non-basic variables. That will be B inverse n. So this will be 3 by 8, 1 by 8, 5 by 8, 1 by 8, 3 by 8, minus 1 by 8, minus 1 by 4, minus 21 by 4, 5 by 4. This is B inverse n. Okay. You require this entire vector to be greater than 0, 0, 0. As long as delta satisfies this condition, my current, as I'm changing the cost of the cost of the or the profit of making beds, my current BFS will still say optimum. Okay, so we will again get a range. This is going to give me three conditions on delta because I will just take what is this? This is 2 minus delta 3 by 8 is non-negative. So if you just you can check, okay, you'll get three conditions of delta. This delta will be between 16 by 3 and minus 48. Okay. So what this says is, so if you convert this to the profit form, so as long as the unit profit for beds, so what is my current unit profit for bed? My current unit, so delta is a change. Okay. So my current unit profit for bed is 52. Okay. So as long as this changes, is in the range. If you convert the cost to a profit, it'll be 52 minus 16 by 3, and the profit will be 52 plus 48. In this range, we will use the same optimal production plan. Okay. Beyond this, we don't know. I mean, we don't know means the solution is going to change, and we'll have to resolve the problem. Okay, because what's going to happen is beyond this range, some of the reduced cost is going to become negative, and it's going to start becoming useful to start bringing them into the basis.
Which step from scratch?
So the question is, do we have to solve the problem from scratch? You can, but you don't have to, because you already have a tableau here, right? You have this tableau, right? So you can use this tableau. The costs have changed. So you have to just this is already, so in the tableau, what do you have? In the tableau, you have B inverse A, you have B inverse B. This is still going to be non-negative. This is going to be valid. What is going to change is some reduced cost is going to change here. So you just have to recompute the reduced cost. Something here is going to become negative when delta is changing too much beyond this range. So you'll get a negative reduced cost. So just calculate it, bring that into the basis, but you can start at this basic feasible solution. Does that make sense or no? Because this solution, when I'm changing cost, the solution is still a basic feasible solution. It is not that it's not because it is still an optimal. It's okay. It's still a basic feasible solution. It may not be optimal, but it is not my polyhedra is not changing, right? When C is changing, A and B are not changing. So it still remains a basic feasible solution for the original primal problem. What changes is only the cost. So primal feasibility is not affected and optimal, and it still remains a BFS. So the idea is what? Suppose delta changes, let's say beyond 16 by 3. Okay. This is 5 point something, right? Let's say delta goes to 6. Some reduced cost is going to become negative. Okay. So one of these variables is going to, you calculate the new reduced cost. Something is going to become negative. You'll bring that into the basis. But the goal is not the goal. The intuition is you you're fluctuating it a little bit, it's probably going to be very close to this current BFS. If you start from the original basic feasible solution where you add the identity matrix with the slacks, again you'll have to resolve the problem, come all the way out there, and then find the optimal. So you're potentially saving a lot of iterations. Right? I mean, it's like saying you already have a good solution for a nearby problem. Use that to start the problem.
I mean, when we make the change, we only substitute the new cost
Yes.
in the
Yes. That's all you change. Yes, that's all you change. The top row changes. You will change the reduced costs, and you will change the objective function because the costs are changing. So objective function will change. You just have to calculate that. Something is going to be negative. So you'll bring that into the basis, and then you will do simplex till you converge.
B is the one that changed, right? You just do that well.
But then you have to when you do B changes, you have to use this thing called in B. You can't start with this primal simplex method that we have learned because when B changes, this one of these can become negative. The left hand, what we are seeing here, but this will all be non-negative. So you have to use this thing called the dual simplex method, which I didn't go through in detail, except it's there in the book. But in dual simplex, what you do is you're going to bring, essentially the idea is, because the reduced costs here are going to be non-negative, but one of this is going to become negative. You're going to identify which variable to bring into the base. It's in the dual phase basically. So that's going to enter, and you're going to find something to remove to leave from this side. Okay. I did not do a complete step of the dual simplex method. It's there in the book. It's basically the same thing as a primal simplex, but just going in the other direction. But just imagine here you're in primal simplex, negative, bring in, take this out. In dual simplex, one of this is negative, bring that in, take this out. I'm sorry, take this out and bring that in. Okay. Okay. Good. Okay, it's 11 o'clock. Maybe we take a break. Uh, let's start after 5 minutes.
So we could have done the exam after the recess week too, but I scheduled it for before recess. Okay. You prefer doing it after recess week? You'll see us there. I mean, if you guys really want, I'm okay shifting it back by one. Everybody's. Okay. I'm not caught up about it. I'm okay if you guys want it. Yes, that's what it's everything. It's not today. I don't feel. Oh, 16. Yeah. No, no, no. Not this one. Yeah. I don't think. Oh. You can also. Yes, that. When you know the connection. No, inside. Yeah. Tomorrow. These are national events. Right? We must decide first. I think let's actually stick to it midterms next week because I need to get a sense of how you guys are doing. So I will, next week there'll be no classes in study. Okay. Okay. And this is what we're covering today. I will not be testing. Listen. Tomorrow, yeah, yeah, that's it's not it's not all depends. I'm not sure what it is that thing that. Don't have a copy of the textbook or you guys don't have a copy of it? None of you agree? Online. Online. No, no. Oh,
Shall we start? Okay, so you can see that the name of the game is to look at the optimality conditions and feasibility conditions and to analyze it. Okay, so I just want to maybe show you with the code. Okay, don't I have the code open? Yeah. So I'm just. Can you see this? It's a bit small. You can see it. Okay. So I'm just showing you the same problem. Okay. I just coded it up. Okay, in Julia, and jump is the code. So I'm using Mosaic here as a solver. I've just coded up the same LP. Okay, it's a maximization. I've written it in maximization form. There are three constraints. I've given some name. They're constraints and variables. I'm optimizing it. Okay, so let me just run this. Hopefully it runs. First time it calls, it takes time, then it'll settle down. Yeah. Okay, so that's the model. It's solving an LP. Okay, it's doing some iterations. It's solving basis and it's found a solution. The value for X is what we saw. You make 18 beds and 12 of the chairs, but no tables. Okay. The objective value is this 1176. Okay. Now, when you solve an LP, okay, and again depends on the software you use. Okay, but in Jump, for example, I get an LP sensitivity report. Okay. And again, it'll depend. If you do Gurobi, there'll be, I mean, you can get all type of outputs from these solvers. Okay. The solver here is Mosaic. Jump is just an interface. Okay. To run these, to write the codes in an easy way. Okay. You can use anything. You can use Python with whatever you like, whichever software you're comfortable with, you can use. But if I look at, for example, this report, so let's look at maybe we did. So this report X1 tells me the change in my this the we spoke about the change in the what is this? This is the change in the B. Okay. So remember we analyzed the B. This this change. Okay. Is it that or what? Sorry, just give me a minute. I'm trying to remember what this is. This is the change in no, actually this sorry, this is a change in cost. No, hold on. This is the change, the minus 90, the 96 and the minus 10.667. Sorry, I'm trying to remember what the codes are doing. The 96 and the minus 10 by this 96 and the minus. So this was change in B. Okay, that's the dual variables. So that's this part. So this is telling you how the change in B should be, what the range of the change in B should be for the current solution to be basis to be optimal. So remember we saw that if B1 changes in this range, 96 to minus 10 points, minus 32 by 3 is this number. Okay, that's the corresponding output. It doesn't change. Okay, this is for the change in cost. Okay, if the cost changes, for example, if the cost changes in this range, we saw the minus 2 to infinity. Remember the minus 2 delta greater than minus 2. In the profit form, it's between 2 to minus infinity. It doesn't, the current basic feasible solution is, the current basis is still optimal. So you are getting this by without resolving the problems. So what's happening is these sensitivity analysis reports are just coming from these optimal tableaus, basically. Okay, so any good code will give you this sensitivity analysis because this information is useful for practitioners. Okay, okay, is that clear? You can try this at your own time, but essentially each of this is that range that we just calculated for delta. Okay, now you can do some more. So I'll show you a couple of other things which you can do. I won't do the computations here, but I'll just tell you a couple of other things. Okay, so you can say, what about changes in A? Okay, okay. This is slightly more tricky in the following sense. Okay. So what, so changes in A. Okay. Let's say I have a particular component Aij. It is changing to Aij plus delta. Okay. So I'm changing a component of A. A is a matrix. I'm taking the ijth component. So that, for example, maybe the amount of time it takes to make do manufacturing for beds, maybe that changes a little bit. Okay. If that changes, how does my solution change? Okay. Now, when this happens, again, there are two things which are possible. Okay. So it could be the case that xj. So if xj was a non-basic variable, okay, remember my conditions. B inverse B is non-negative. C n transpose minus CB transpose B inverse N is non-negative. These are my two conditions, right? Okay. So if the xj was a non-basic variable, okay, that means it doesn't show up in the basis matrix. Okay. So this AJ column, this AJ, this entry you're changing, then the AJ column only shows up in this N matrix, right? Because I'm changing. I mean, what is happening? And what is A matrix? One of the entries is changing. Okay. That entry which is changing, it corresponds to that this entry is changing in a particular column. This column shows up in this part, N. It doesn't show up in B because the basis, the this xj variable is not part of the basis basic variables. Right. So the B matrix will not be affected. Right. If B is not affected, again you will get a range. Because these are just linear conditions. If some component here is changed, it's like again you'll get a range on delta, and again you will find that range on delta. Okay. I'm not going to write this down, but basically you can find, so what is going to change? Okay, because basically you need to check. Essentially, only the jth component here changes in this in this term basically. So you have to just essentially you have to just check Cj minus Cb transpose B inverse this Aij component which is changing. So this will become Aj, the jth column, plus delta times Ei basically. Okay. So this has to be non-negative, which is going to give you a condition. Okay. So what am I writing here? What this many of these columns here are not changing. Okay. So those reduced costs are already non-negative. Only the one of the columns here is changing. Okay. So I have to figure out the ith, the column corresponding to the non-basic variable xj is changing. Okay. So if you write down the condition, you will get a condition like this. This will give you a range on delta. Okay. So I'm not going to calculate it, but hopefully the idea is clear. Okay. Okay. The difficult case, okay, again, beyond this, you can use, so beyond, so if the reduced cost becomes negative, beyond you can use primal simplex. Okay. The difficult case is if xj is a basic variable. Okay. Then analysis is complicated. Okay. Why is this the case? If my xj was a basic variable and aij is changing, it's affecting my basis matrix. But my optimality conditions I have basis inverse. Okay. If you change a component of a matrix, the inverse of the matrix changes in not in a linear fashion. Okay. A matrix inversion, if I take a matrix and I change some component, I mean, so you'll have to go to some It results from matrix analysis for this. But essentially, linear changes in the matrix entry is not going to have a linear change in the inverse matrix entries. Okay. So the analysis is complicated, and then people have come up with some analysis techniques for this, but you can basically resolve the problem. Okay. But I don't want to get into that here. Okay. This is not the key for this class. Okay. Except saying that when A changes, the analysis is a little bit more complicated because things don't change here in a linear fashion. Okay. Hopefully that's clear to you. Okay. Okay. Is that clear? Okay. So next, 11:20. So I'll probably do maybe the new variable. I won't do new constraints maybe. Okay. It's there in the notes. You can look at it. Okay. I'll do one more example and then I want to tackle two other issues. Suppose I've got a new variable being added to LP. Okay. So what is happening now? I'm solving an LP, but now I've got some new manufacturing opportunity. So maybe instead of making beds, tables, and chairs, maybe I can make sofas. Okay. So I've got some new possibility. Maybe that comes with a cost with a cost of Cn plus 1, but it requires some resource, which is so there's a column vector. Okay. So I've solved my LP originally, but now I've got this new opportunity that has shown up, and I want to know, should I be using this opportunity or not? Okay. Is it clear what's happening? LP is modifying. I'm now bringing in one new variable to the LP. Again, I can resolve the problem, but I already have an optimal solution to my original LP. Okay. So what's my optimal solution to my original LP? X star. There are two parts to this. Okay. X star is basically the basic variables are B inverse B and non-basic variables are 0. This is to my original problem. So one thing I can do is I can say this xn plus 1, I can simply force it to be 0. Okay, I can say I will not use this opportunity. Okay. Okay. So if we do this, if we use this particular condition, so this is clearly feasible for the new LP. Okay. Okay. And it's going to be a basic feasible solution because Bx is equal to B. So xn plus 1 is like putting in a new non-basic variable. Okay. So what do I have to check? I have to check by doing this, what happens to the reduced cost for this new vector, in this new variable. So I need to check. So we need to check the reduced cost, which is what? Cn plus 1 minus Cb transpose B inverse An plus 1 is non-negative. Okay. So because right now xn plus 1 is not being produced, I already have my basic variables. So xn plus 1 is a non-basic variable. I have to check the reduced cost for this non-basic variable because I'm using my current basic feasible solution and simply bringing xn plus 1 into my non-basic variables. I have to check this condition depending on the cost for xn plus 1 and the resources it requires. If this is true, original solution and this new solution making it equal to 0 is optimal. Right? Because the reduced costs are non-negative, that's my optimality condition. If not, so if this condition is true, if star is true, if star does not hold, then I have to use primal simplex. Because I've got a reduced cost which is negative. That means that this new opportunity, the costs it is taking and the resources it's using up, somehow it's making it attractive to make this product. So I should be making this product and taking out something from my current portfolio. Okay. So it's just a matter of computing this cost. Okay. Is that clear? So again, just using the optimality conditions, nothing else. Okay. Okay. Now in the notes and in the book, there is also cases when you add in new equality and inequality conditions. Okay. I provided it in notes, but I think I will not do it at this point. I want to get to a couple of other issues here which I want to discuss. It's there in the notes, it's there in the book. You can read it at your own time. Okay. But there is also analysis. Okay. So maybe you can try this. You can read this at your own time. Five. So adding in, so new constraints being added in. Okay. Read on your own. Okay. It's there in the book. Okay. But I want to cover a couple of other things basically. Okay. Okay. Any questions on this part so far that we have discussed with sensitivity analysis broadly or even specifics here? Okay. Then let's talk a little bit about, so I want to talk about two other things. So one is, I want to just talk a little bit about how is things depending on these parameters, especially B and C. Okay. So next thing I want to talk about is, so one change in B. So two, so we'll talk a little bit about global dependence on parameters. Okay. That means more broadly, if things don't change with small things, but there's a how does the optimal value depend on the parameters? Okay. So we'll first do this for B. Okay. So dependence on B. Okay. Let's remember what the primal is. So my primal is to minimize C transpose X subject to AX equal to B. So standard form, X non-negative. Okay. I'm thinking about B now is a parameter for a fixed B. I'm computing an optimal solution. So this Z star of B, when I write it like this, so parameterized, so optimal value as a function of B, okay, or parameterized by B. Okay. So think about C and A being fixed. It's a standard form LP. As B changes, how does my optimal value change? Okay. Maybe it's small changes. We did the analysis. If I change a particular component, if I change a single component, we saw how things change. Okay. And we got ranges in which the basis will be optimal. If things change beyond that, things will optimal solution changes. But more broadly, how does the optimal value look at as a function of B? Okay. So we'll discuss that next. Okay. Okay. So first thing is, it might be the case that this problem is infeasible. Okay. You might choose a B that there is no AX equal to B where X is non-negative. Okay. If this problem is infeasible for a minimization problem, the optimal value will be plus infinity. Okay. So we are of course interested in problems where there is a feasible solution. Okay. So I'm just going to define, let S be the set of all B such that there exists an X non-negative with AX equal to B. Sorry, yeah. Okay, so I'm defining a set S as a set of all B's, vectors B, so that there is a feasible solution. Okay. So the first thing you should be able to observe by now is this is the, so this S is actually a polyhedron itself. Why? These are linear constraints. So if you think about X and B, okay, these are linear constraints in X and B, right? So S is nothing but S is a projection of a polyhedron. right? Linear constraints involving X and B. I'm projecting this entire set, X non-negative, AX equal to B, onto the space of B, all B. Okay, so S is a projection of a polyhedron, which means, remember from when we did the Fourier-Motzkin elimination ideas, therefore S itself is a polyhedron. Okay, and more broadly, because it's a polyhedron, it's an example of a convex set, and therefore a convex set. Okay, so the set of values B where it's feasible, where the LP has a feasible solution, itself is a convex set, and in fact, it's a polyhedron. Okay. Okay. So we are interested in understanding on this convex set or on this polyhedron, how does Z star of B depend on B? Okay, that's the question. Okay. So I'll give you we will understand the structure of Z star of B. Okay. But is this clear? This is going back to, so recollect, this came from the Fourier-Motzkin elimination. When we did Fourier-Motzkin elimination, we saw that the projection of a polyhedron itself is a polyhedron. Okay. And this is a projection of a polyhedron. Okay. So the only thing is, think of B now as a parameter. Okay. Okay. In the past, B has always been a fixed set of numbers. If I fix a B, there's a particular solution, a different B, there's a different solution. Many of the B's might be feasible, some B's might be infeasible. If I look at every B which is feasible, of course, some B's might have the same optimal solution, some B's may not. So as the B changes, how does the optimal solution look like? Or how does the optimal value look like? Okay. Okay. So remember okay. So we have written the primal. So the dual is what? The dual is maximize P transpose B subject to P transpose A less than equal to C transpose. Okay. So we're going to make an assumption here. So for keeping the analysis here is clean. So I'm going to assume that the dual is feasible. Okay. So I'm going to assume throughout that dual is feasible. Okay. So dual is not, so we don't have this issue of, infeasibility in the dual basically. Okay. So if the dual is infeasible, then you can have things like the primal being infeasible or the primal being unbounded. But I'm going to focus on the case when the dual is feasible. Okay. It just keeps the analysis simple. Okay. Okay. If the dual is feasible, then this Z star of B, okay, is going to be finite for any B that lies in the set S. Okay. Why is this the case? So remember, we have strong duality. Okay. B in S is primal feasible solutions. So whenever B is in the set S, the primal is feasible. The dual is feasible. Okay. So you don't have this issue of one being unbounded, basically. Okay. So this is always going to be finite valued for any B in the set. Okay. Now we're going to look at the structure of this. Okay. So how does this look? So for any B in S, so I'm going to use duality to my advantage, because remember, in the primal, B is showing in the right hand side, but in my dual, the B is showing in my objective. So Z star of B from strong duality will be maximum P transpose B subject to P transpose A in S. So this is from strong duality of LPs. Okay. But the dual is feasible, and in this set, everything is finite. Okay. So I don't have things going off to unboundedness. I don't have things going off to minus infinity or whatever. So your optimal solution has to be one of the extreme points of this set. Okay. So maximum of P1 transpose B1, sorry, B, P2 transpose B up to Pn transpose B, where P1 up to Pn are extreme points of the dual feasible region. Okay, so this is a dual feasible region. It doesn't depend on B. Okay, in the primal, the feasible region depends on B. In the dual, the feasible region depends. It's doesn't depend on B. It depends on A and C. So this feasible region is a fixed feasible region, as even if B changes. I take all the extreme points of this feasible region. I know from LP theory that the optimal solution will be one of these extreme points. Okay, so we have ZB. So Z star of B is a maximum of many extreme points. Okay, if I give you each of this is a linear function in B. If I take the max of many linear functions of B, what type of function is that? Piecewise linear. Is it convex or concave? If I take the max of linear functions, convex. Okay, when you think of max, you have many linear functions. The max will be a convex function. Okay, so therefore Z star B is a piecewise linear convex function. Okay, and of course finite valued for any B in the set S. Okay, so how does this look? If you think about how this looks, okay, I'm just going to, I mean, of course, B is in, remember, B is in dimension M. Okay, so AX equal to B is a vector in dimension M. Okay, so B is changing it, and this set of feasible B's is a polyhedron. On this set, Z star of B, which is a number, looks like a convex function. In fact, piecewise linear convex function. But if I try to parameterize B by B plus lambda times D, okay, just because it's difficult to visualize in multiple dimensions, think about B being fixed and D being a fixed vector and changing lambda. Okay, so if I think of this as Z star of this lambda now. Okay, so I'm parameterizing by a single number. Okay, so I get every dual extreme point will give me a particular linear function of B. Okay, so this will look like one linear function, a second linear function, a third linear function, a fourth linear function, and so on. Okay, so this, for example, might be P1 transpose B plus lambda D. Okay, this one might be P2 transpose B plus lambda D, P3 transpose B plus lambda D, P4 transpose B plus lambda D. Okay, each of these is a linear function, right? A linear in lambda. Okay, if the dual extreme point is fixed, it's a linear function. Okay, P transpose B will be a constant, lambda, and then there's it's just a function, linear function. What is the Z star of B? Now I'm parameterizing this by a single parameter lambda because I can't visualize it otherwise. So this will simply be this part. Okay. So on this part, the dual P1 is optimal. On this part, P2 is optimal, and so on and so forth. So it basically is partitioning the feasible region, the space of B, so that each of the dual extreme points is optimal. Okay. And when you have a point like this, you have two dual optimal solutions. Okay, so multiple dual optimal solutions, which is generally going to be primal degeneracy. Okay. Okay, but this is important. So you can think about, so the optimal value is a nice convex function and piecewise linear convex function of B. Of course, there is one challenge here, that writing it in this form is good from a technical, I mean, from a technical perspective, I can write it in this form. But remember, the number of extreme points can be exponentially large. Okay, so it might be that this has the number of pieces here are very, very big. Okay, because number of extreme points of a polyhedron can be very high. Okay, but it is a piecewise linear convex function. Okay, Okay, any questions there with that dependence? So optimal values of LPs has a nice dependence on B. Okay. Okay. Now you can do a similar analysis for C. Okay. So can you guess what the dependence on C will look like? Z star C. You should be able to, I mean, suppose I'm changing my cost and I'm minimizing cost. How do you think Z star of C will look like as a function of C? So we saw that Z star of B is looks like a convex function of B for C. So it's going to be a piecewise linear but concave function in C. Okay. Why is this the case? Okay, again, we can do the same thing. So for the duality, so remember the dual is maximize P transpose B. Now, of course, in the primal, C is only in the objective. So it's not the 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 primal space, the feasible region is not affected by C. Only the objective is. Okay. So again, you can look at so we can so to define the space of C where this number is finite, okay, I can look at points where the dual feasible region is basically so to define the space, okay, maybe I'll just to keep this so what are we going to do? So suppose actually maybe just to so suppose the primal feasible region has extreme points, let's call it x1 up to xk, okay, and then again I'm going to focus on the case when this thing is got a finite optimal value. You can identify that space by looking at, again, that's a convex set. So you can go to the same argument like this, okay? You can define the set S if you want, okay? Except now you will look at the dual feasible region, okay? Maybe I should do that, okay? Let's do that. I don't want to. So let T be the set of all C such that there exists a P such that P transpose A is less than C transpose, okay? So again, T is a polyhedron because it's a projection of a polyhedron, okay? So on this set, so whenever there's a dual feasible solution, okay, so suppose the primal is feasible now, okay, then Z star of C is going to be finite valued for any C in T. Okay, so again, I'm trying to eliminate the unboundedness case. So on this set, so this is all the C which is dual feasible. So I've got a dual feasible solution. So I've got a dual feasible solution. Suppose the primal is feasible too. So I will be in the case of strong duality when I've got a finite optimal value. Okay. So I've got on this set, C and T, I will be finite valued, optimal valued. Okay. So with finite optimal valued, then let me eliminate this. If you look at what Z star of C will look like, Z star, so for any C in the set, this is a nice convex set, it's a polyhedron. Z star of C, which is to minimize C transpose X subject to AX equal to BX non-negative. Because it's finite valued, I can just focus on, so I don't have any of these unbounded directions and it's feasible. So I have to look at only the extreme points. Where x1 to xk are the extreme points of the primal feasible region. Extreme points of the primal. Okay. feasible region. And what is the minimum of, so this is a linear function in C. If I give you many linear functions and I ask you to find the minimum, that's a concave function. Okay. So this is a piecewise linear. So therefore, Z star of C is piecewise linear concave and finite valued for any C in the set T. Okay. So if you try to plot this, it would look something like this. So if you take C and you write this as C plus lambda D, again, I'm making this in one dimension. I might have many linear functions. So now my Z star of C will be sorry, I should be careful in my drawing. So this, for example, is the case when, so this Z star of lambda now for one as a function of one parameter. So this is the case when, let's say, C transpose X 1 plus lambda D. This is, let's say, C transpose X2 plus lambda D and so on. C transpose X3, the third extreme point plus lambda. What am I doing? The C plus lambda D. Sorry. It should be C plus lambda D transpose X1, C plus lambda D transpose X2, C plus lambda D transpose X3. So this is the case when the third extreme point is optimal. This is the case when the second extreme point is optimal. This is the case when the first extreme point is optimal. And these points are points where you have multiple primal optimal solutions. Okay, but the piecewise linear concave function, again, you get, so it's got a nice dependence on C. Again, there are too many pieces, linear pieces. Okay. Okay. And I'm not talking about dependence on A because the the objective function doesn't depend in a nice, like you don't have this convexity or concavity property that you got with the, so in my LPs, this dependence on the A and on the B and the C, you have got this concavity and convexity properties. The dependence on A is not as nice. Okay, because you can see also, think about the optimal value. What is the optimal value for basic for LPs? CB transpose B inverse B. That's a dependence on the matrix inverse. It cannot depend. I mean, you're not going to get properties like convexity and concavity and all this stuff easily. Okay. If A changes even in a linear fashion, this is not going to be a nice, you know, you're going to lose properties basically. When you do inverses of matrices, you're not going to have these nice properties coming through. Okay. So the dependence on A is more complicated. Okay. You don't have such nice structures. Okay. Any questions with those two? So I want to discuss one final thing before we end for today. Okay. So okay. So let me discuss one final idea. It's not there in the book, but I just wanted to mention this because see the goal is of sensitivity analysis broadly is what when parameters are changing in the LPs, you are hoping to understand what happens to the optimal values and optimal solutions and try to somehow figure out if it's changing, can you quantify the change? Now, there have been in the last 20, 25 years, a lot of interest in trying to protect against changes. So, you're going to implement a solution in practice. Maybe the A, B, and C are going to change a little bit, or you don't know it exactly. So, you still want to implement a solution and you want to do this in a nice manner, right? You want to do this so that it is robust to changes in the data. So one idea that has been quite popular in the last 20 years or so, and I think I want to show you a basic model there because it's an application of duality, is this idea of what's called robust optimization. Okay. And there are other ideas. There's something called stochastic optimization, and there are, there's some other techniques out there. But I want to just talk about one simple model here. So the idea is what? The data is changing. I want to protect against the changes in the data and still find a good solution. Okay. So I want to protect against all possible perturbations in the data and still perform as well as possible. Okay. Okay. So that's the general goal. You want to be robust. Okay. You think things might change within like maybe 1% changes can be there in the parameters. How do I plan for that and still make a good decision or a good solution X? Okay. So I'm going to show you a very simple model here, just the most basic model. There are full books on this topic. Okay. There's a full book on robust and in fact, now there are at least two books I know on this topic on robust optimization. I can point you to it if you want. But in the last 20-25 years, there's been a lot of research in this area. And there are many models on this. I'll show you one model. Okay. So think of an LP of the following type. Maximize C transpose X. I'm just going to change the formulation a little bit. That's fine. All LPs can be written in one of these forms. I'm going to focus on this form for this discussion. So let's say I've got a maximization problem and I'm trying to I've got some constraints AX less than equal to B. Okay. So A is a matrix. Okay. Suppose each entry of Aij of A can lie in an interval. Okay. So let's say actually the value of Aij can take a value Aij, but maybe it can go down by some number or it can go up by some number. Okay. So this Aij hat is a non-negative number. Okay. So what does this mean? Let's say my nominal or my basic value of Aij, let's say is 3. I think this number 3 might change between 2.8 till 3.5. Or for things here, I'm keeping it symmetric. So let's say 2.8 to 3.2. I don't know what exactly my Aij value is. It can be any number in this range. Okay. So when you solve an LP, you have to give me a particular value of A, right? Only if I give you a particular value of A, I can use the LP method, simplex method to solve the problem. But if I'm changing A, every value of A might give me a different X. So how do I find the best solution? So what robust optimization does is the following thing. It plans for the worst case. Okay. So you plan for the worst case and find the best solution. Okay. So here's what is called the robust LP. Okay. You maximize your objective that you're interested in. Okay. Except now, when you write Ax less than equal to B, A is changing. So you want this to be satisfied for every value of Aij which lies in this set. Okay, so what am I saying here? So I've got a constraint. I want to maximize Cx, C transpose X. I want this Ax to be less than equal to B. But I don't know what exactly A is. So I'm writing that by A tilde. Okay. A tilde can take any number in this set. Each entry can take an upper bound and a lower bound. It can lie between these two upper and lower bounds. It can be any one of them. I want to choose an X so that regardless of what A tilde shows up, I'm still going to be feasible. So this says feasibility is Ax less than equal to B. So I'm ensuring feasibility by ensuring this is true for every value of A in the set. Okay. Now, what is the difficulty in this LP? The thing is, now I don't have a single constraint, but I have a constraint for every possible A tilde. And there is not only a finite number of them, there are infinitely many A tildes possible because I'm in a box. Suppose one entry changes in this is my original values, but it can lie in this set. Any of these A's can occur. Okay. So I'm planning for many possibilities in a box. Okay. The good thing about LP is we have duality for a rescue. Okay. And actually, there's a problem where actually here you don't, yeah, I mean, actually, in this problem, okay, it's even easier. You can rewrite this as maximizing C transpose X subject to, here we don't even need duality, I think. You can rewrite this as, okay, so let me write one constraint, summation J. If I want a condition, if I want this, actually, I don't even need duality here. Okay. Uh, okay, so what are we doing? We are rewriting this as, I want a condition to be satisfied for every possible value. Okay, it's a less than equal to constraint. If it has to be, something has to be less than equal to some number, the maximum of it has to be less than equal to that number. Okay. If I require the maximum of this to be less, so take the ith constraint. Okay. The right hand side is bi. I want the maximum value for the left hand side to be less than equal to bi. But because I've chosen each aij can lie in an interval. So for every term, and this is a linear, it's a linear combination, I find the maximum value for every individual linear term. So I'm basically maximizing this number within this range for every individual linear term. Okay. If I'm trying to maximize a linear function on an interval, the optimal solution has to be at one of the two endpoints. To either be this endpoint or this endpoint. Okay. A polyhedron in one dimension is just a line segment. Okay. So this will be the same thing as maximizing C transpose X subject to, it can either be the lower bound or the upper bound. It's a linear function, right? In a one dimension, a polyhedron can only be a line segment. So it can either be the optimal values, either this point or this point, the lower bound or the upper bound. Okay. It depends on what xj is. Is it positive or negative? Okay. If xj was positive, this would be the optimal solution. If xj was negative, this would be the optimal solution. Okay. So what you will get here is aij xj plus aij hat, absolute value of xj is less than equal to bi for all I. Is that clear what I did there? No. If I want to maximize, let's say a times x, okay, subject to, let's say a between a tilde between a plus a hat and a minus a hat, this should be exactly a at ax plus a hat absolute value of x. Why? Because if x is positive, I will choose this one. If x is positive, I'll choose this one. If x is negative, I will choose this one. Okay. And when I negative and negative together will give me a positive coefficient. Okay. Is that clear or no? I am not sure if you're looking. Yeah, I'm not sure if you're following me or. Okay. But if you look at this constraint, this is not an LP, but this is a convex function, piecewise linear convex function. You know now how to rewrite this as an LP. You can rewrite this as an LP. What? What do we do? Maximize C transpose X subject to, you can simply bring in a new variable here. You can write that as summation J Aij Xj plus Aij hat Yj less than equal to Bi for all I. And all you have to do is Yj, you have to yj has to be greater than equal to the absolute value of xj. So it should be greater than equal to xj, yj greater than equal to minus xj for every j. So what we are doing is we are adding in a few more variables, as many as the number of A components. Okay. But this is an LP. We started with an LP originally. We also have an LP. It's a slightly bigger LP, but this LP protects for all possible realizations of A. Okay. So it turns out that people have been very interested in understanding how to find good, robust solutions for LPs that are not affected by too much perturbations. Okay. So it turns out in many cases you can use, so in this case, I didn't use duality, but if you, for example, if you let A lie in a polyhedron, you can use duality actually. Okay. So there are tricks. Okay. So there have been a lot of interest in this. So sensitivity analysis is what is called post-hoc optimality. You have an optimal solution, you're changing your parameters, you want to know how the optimal solution changes. Things like robust optimization are trying to find a good solution, planning for perturbations. Okay. And so there are different modeling frameworks available here for optimization. Okay. Um, I just wanted to introduce it to you because I think the idea here is quite straightforward. We're just using a simple what's called an uncertainty set, and you're getting a piecewise linear convex function, and you can reformulate this as an LP. Okay, so you're still within the same class of linear programs. Okay, there are a couple of books on robust optimization. If any of you are interested later on, I can share it with you. We won't do this in this course. Okay, but I do want to point out to you some ideas which are beyond the class itself. Okay, okay, we'll stop here. If you've got questions, you can ask me. Otherwise, I will see you on Friday. Friday, we'll talk about large scale optimization.